Hello and welcome. My name is Aaron Vraniak, and I'm going to be teaching you a lesson on inductive reasoning and conjecture. This corresponds to Chapter 2 and Section 1. Our main goals are just making conjectures based on some patterns in numbers or geometric figures, as well as finding something called a counterexample in order to test the validity of the conjectures or a conjecture. So the first things we're going to talk about are some inductive reasoning and some conjectures. What are those? If you're following our highlighting guide, you should highlight this one in green. That is a vocab or keyword. Same with this, it's also in green. And any example I like to highlight in blue. So when you're looking back at these notes, you can highlight them and look exactly where are my vocab terms that I kind of need to know. So what is this inductive reasoning? Well, inductive reasoning is the process of observing patterns or specific examples in numbers. We're looking for patterns. It's a process of observing patterns. And it's kind of making some sort of generalization, which is called a conjecture, based off of these observations. So an example, really quickly, is like if I have the number 5, and then I go to 7, and then I go to 9, that should be a comma, and then I go to 11, what would you assume would be the next number? Well, if you said 13, you're probably right. That's a good educated guess or generalization of what will be next. So this idea of inductive reasoning is this next number, the next number appears to be, let's say, TO to be 13. Now, does it have to be 13? Well, no. We're making a guess based off of patterns. So it doesn't have to be 13, but a good guess would be 13. This leads us to a conjecture. What is a conjecture? So this conjecture is that educated guess or statement that is believed to be true based on that observation or pattern or evidence. So we're making this educated guess that's believed to be true based off of observations, patterns, and evidence. Those are huge things. They're usually formed using this inductive process, this inductive reasoning. And while they can seem likely or reasonable, they are not proven facts. So that's something that you should probably know. They are not proven facts, meaning it could be wrong. Like it rained today, it rained yesterday, and the day before, and the day before. Will it rain tomorrow? Well, it rained 4 days in a row. That doesn't mean it's going to rain tomorrow. It could, but it doesn't have to. It's not proven. So that is kind of like a conjecture. So going back to that example, which we're going to highlight again in blue, because we're going to basically use the same example of 5, 7, 9, 11, dot, 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 dot. Our conjecture is that we increased by 2. So I didn't make a nice dot there. So our conjecture is we increased by 2, which you think about it, that's add 2. We're adding 2 every time. That is a conjecture, and we could probably prove it. So looking at patterns, we're making conjectures off of our inductive reasoning, what seems to be true. So the first few examples are very simple, and it's just kind of walking through what should be the next pattern, or the next numbers in the pattern. So let's start by highlighting example 1 here, and it does give us some key information that is not necessary for just looking at inductive reasoning. If I was doing deductive reasoning, these two words or sequences tell us a lot. What we're going to do is find the first 3 terms, or given the first 3 terms, what are the next 2 terms of the sequence? So what would those be? What would those be? And I'm going to think inductively, so I don't even need these words arithmetic, which this just means we're adding the same value, or subtracting, if you want to think of it that way. It's adding a negative, which is subtraction. How do I get there? So how do I get from 17 to 14 to 13? Well, it looks like I am subtracting 3 to get there, subtracting 3. So I keep subtracting 3 and subtracting 3 to get to the next term. So that looks like, what is 11 minus 3? Well, that is 8, positive 8, and then 8 minus 3 gives me 5 for those next 2 values. Now the next one down below is geometric, which means multiplying by the same value every single time. Again, this is not really needed. That's more so needed for what we call deductive reasoning for those. These are some common sequences that you've learned about at your younger years, and we'll learn again in Algebra 2, and we'll probably focus on later this year as well. So if I look at from 2 to 10 to 50, what am I multiplying by? Well, I am timesing by 5. So times by 5 here, 2 times 5 is 10, and then 10 times 5 is 50. And if I keep multiplying by 5 every single time, my next numbers will be, well, what's 50 times 5? Well, that's 250. Now I take that number times by 5, which that gives me 1,250. Those are what I'm inductively thinking are the next ones in that pattern. Now, that is technically deductive reasoning, and we'll talk about that later. That's something we get into in section 4. But if we just look at the numbers, we don't care about what this vocab term is yet. We can just say, well, we're jumping up by timesing by 5. So the last thing is, well, we're starting up here with this backwards L of circles, and it looks like it's lessening one here and one here, and it does it again and again. Now, what would be the fourth pattern? So let's just draw that fourth pattern, and how you can do that is like, well, if we delete that ball, we're left with 1, 2, 3, and then it just goes to the left a couple. So again, it has 2 and 3, I like 3 and 4, so it kind of has that number there. And we have a total of 5 circles if we just count this here. And you can keep going less and less and less. So if I wanted to go one more less, I get rid of that, and there's 3. And then if I want to go one more, there's 2 left, and then there's just 1 left over. You get rid of those 2, and 1 left over. So let's see if you can try this next one on your own, check your own understanding. So what would be the next 2 terms of this type of sequence? And I'll pause it here, or have you pause it here to try those. So hopefully you got 20 and 10, and a conjecture, you can think that inductive reasoning, you're thinking, well, I just divided by 2 every time. So 160 divided by 2 is 80, divided by 2 is 40, or halving if you want to think of it, and taking a half of everything, which is actually caters to what geometric is. You have to multiply by half. And we'll talk more about that when we get into sequences and series, which more too alludes to Algebra 2. So the next thing, or the last thing, is something called a counterexample. And this is what I want you to highlight in green, counterexample. And I didn't give a definition here, but what we are going to do is write down this definition right here. So a counterexample is going to prove a conjecture is false. This proves a conjecture is false. And that's not the definition, but it's what it does. So a definition of this is like, it's going to be an example that counteracts what we think is true. Like, meaning it's proving it's wrong, which is where we say proves the conjecture is false. So we're going to show that each statement is false. So we know these statements are false. All of these statements are false that we're going to be doing. We're just going to prove they're false by writing in answers that are going to make it false. Now, if a length of xz is 40, so let's just quick draw xz. So I'm going to draw from x all the way to z right here, put a couple dots. This is x, x and z right there. So we know this length from here to here is going to be 40. So we're given that. We know that the length is 40. We also know that point y lies on that. So put it right there somewhere. Now, the then part says that xy has to be 26. So this length has to be 26 and yz has to be 14. Is that true? Does this have to be 26 and 14? Well, the way I set it up, it doesn't even look like this one is bigger than that one. So we could just put in any numbers that add up to 40. So I could say that this is 10 and this is 30, which it kind of looks like that maybe based off of the way I drew it. So would you agree that 10 plus 30 is in fact 40? And that is a counterexample. It's actually proving that this is not the only answer. So having this statement and then proving it wrong is what the counterexample does. So let's go ahead and do a couple more of those. 3 more to be in fact, and then I would like you to try some on your own, and then we'll be done for the day. So if we know angles 1 and 2 are complementary angles, meaning angle 1 plus angle 2 add up to 90 degrees. That word, remember from our vocab quiz, complementary, two angles that add to 90. Then one of them must have a measure greater than 45 degrees. Well, again, these are all false, and we want to prove a counterexample, like make it so that it's true, or the statement above is false. So if we think about it, if it's greater than 45, it's like 46, 47, could be 45.1, but it does not include 45. So if I say 45 and I say 45, well, what's 45 plus 45? That is in fact 90 degrees. Those are both not greater than 45, but they're also adding up to 90. So this is a counterexample. So let's do another one. Measures of P, Q, and R add to 180. So we have three angles. They add up to 180. Then all of these angles must be acute, meaning they have to be less than 90 degrees. So these angles must be acute. So every one of them has to be less than 90 degrees. Well, let's just pick one bigger than 90 degrees here. So if I do that, let's just say this is 110 degrees. Well, I could just say this one's 30 degrees, and that's 140 total, and I just need 40 more. So therefore, this is obtuse, and those two are acute by those definitions. So this one, remember, is obtuse, and these ones acute, and this one is acute. Therefore, this is a counterexample to the fact that the angles must all be acute, which they are not. One is not acute. Then our last one is the perimeter of a rectangle is 28. So we have some rectangle. We know that if we walk around the rectangle and add up all of those, it's going to be 28. So the perimeter is 28. One thing about rectangles, if we know this length, it's also that length. If we know this length, it's also that length. So rectangles, those sides opposite of each other are equal. And just say that all adds up to 28. Well, if we say the perimeter is 28, we're saying that the length is 7 and the width is 7. So does this have to be 7, 7, 7, 7? Well, in fact, no, it doesn't. I can in fact draw a rectangle with a perimeter of 28 without those. So I could just say that, let's say that's 12 and 12. Well, that's 24. Now, almost to 28, I need 4 more, which let's just say put 2 and 2 here, which that gives me a perimeter of 28. One thing again about rectangles, the opposite sides have to be equal. Now, if I asked you this on a question or on a test or something, I would like you to draw the picture just to show it. So in this case, our length of this would be 12 because it's 12 long, and the width is 2. So that would be a counterexample for that. So I would like you to see if you can try these last two on your own. So check your own understanding here. Pause it. I'll have an answer for that in a moment. And then please summarize on your own what we did as our main ideas. So these are two counterexamples to that. First off, just remember that says area. So area is length times width of a rectangle. Because like 12 times 3 is 36. We could also do like 4 times 9. 4 times 9 is 36 as an area. So there's other ones you could do. You could do any type of decimal answer you want, but just easy numbers like that is better. You could do 6 and 6 too. 6 times 6 is 36. So there's a lot of correct answers in this case. Not always, but in this case there are. So for this one, remember this whole angle opens up to 56. It doesn't have to be 28 and 28. We could do 40 and 16. That adds up to 56. So any two numbers that add up to 56 that aren't 28 and 28. So then just summarize your main ideas here.